Hi, my name is Russell Lee, and today I'll be presenting competitive bidding strategies for online linear optimization with inventory management constraints. And this is a work together with Yutao, Lin, Mohammad, and Ramesh. So in the setting of online algorithms, the problem inputs arrive sequentially, and the online algorithm must take an action at each step without knowing future input. Since the algorithm relies on current and past inputs alone, it's very difficult for the algorithm to have optimal performance. To analyze the performance of online algorithms, we compare the cost against the optimal offline algorithm, which knows the entire sequence of inputs. This metric is known as the competitive ratio. And since the cost of the online algorithm is always at least the cost of the optimal offline algorithm, this ratio is always at least 1. And the lower this competitive ratio, the better. In particular, the problem we'll talk about today is the online linear optimization problem with inventory management. So this problem has two settings. One where we must purchase an asset from the market with time varying price P of t in order to satisfy some demand D of t. The other setting is where we must sell an asset to the market based on a time varying supply U of t. But in both cases, we have access to a local inventory B of t that can store the asset for future time slots. In this online problem, the price, demand, and supply are known for the current slot, but they're unknown for future slots. In that case, the goal is to decide how much of the asset to buy X of t or how much to sell Y of t so that we can minimize cost or maximize profit. These problems, they're constrained by demand and supply dynamics and the changing inventory levels over time. So these two problems, they're well studied and are actually extended versions of the K-min and K-max search problems studied in the work of Lorenz, Panagiotou, and Steger in 2008. In these problems, the goal is to buy or sell K items with an online arrival of prices. Some more recent work in Symmetrics 2020 and 2017 developed algorithms with optimal competitive ratios for the setting with inventory management. And a practical motivation for these problems is energy storage and the electricity market. In this diagram, a market participant must satisfy the energy demand DFT of a large-scale customer such as a data center. The electricity quantity X of t must be bought from the market at price P of t, or discharged from an energy storage system. In addition, any surplus of electricity can be stored for future use. However, in practice, the current price P of t might not be always known to the market participants. In the case of a bidding scenario, participants must offer bids on electricity, and what's called a clearing price P of t is only made known after the participants have submitted their bids. Since P of t is not known for the incoming time slot, the previous algorithms cannot be directly applied. And for today's presentation, we'll discuss our algorithm for the demand setting in the bidding scenario, but our paper provides some analysis for the supply setting as well. So first, we can go over a basic single bid scenario. The participant begins by receiving the demand D of t, but they don't immediately know P of t. They must make an offering bid consisting of a price P and a quantity Q. And after submitting the bid, the market price clears and P of t is announced. So if P was greater than or equal to P of t, the participant must buy quantity Q at the clearing price P of t. Otherwise, the bid is rejected and nothing is bought. So in fact, because of this, the single bid scenario is somewhat trivial since the demand constraint will compel the participant to submit a bid that cannot be rejected. However, the multiple bid scenario has much more design space for deciding how to submit bids. In this setting, the participant submits m bids on the asset, each with price and quantity P sub I and Q sub I. Now, after all m bids have been submitted, the market price clears, and any bids with price P sub I greater than or equal to P of T will be accepted. Then the participant must buy the sum quantity of all the accepted bids. Now, since the bidding scenario has less information about P of T than the regular online scenario, the best possible bidding strategy cannot be better than the optimal online no bidding strategy. However, we position our bidding strategy around the optimal online algorithm so that we can be as close as possible to the online optimal with some measured degree of error. So we take a look at the optimal online algorithm. This algorithm is based on a threshold function. And for future comparison, this algorithm dem on is alpha competitive. This decreasing threshold function G, it maps the price P to a procurement level between 0 and B, where B is an inventory capacity. P min and P max refer to known lower and upper bounds for the clearing price. In addition, we have a reservation price Xi, which retains the last price at which we bought the asset. Now, this reservation price, it's maintained by an update rule. So first, at each time t, we consider only the prices that are less than Xi. Then the procurement amount x of t is given by the difference between the threshold value g of p of t minus Xi. And here, we also purchase more if necessary in order to cover the demand. Next, we update the reservation price Xi to P of T, and if necessary, Xi will reset if the storage level becomes empty. Now, since x of t dictates how this threshold function basically results in the optimal online algorithm, we decide to use the same g function when we are designing a bidding strategy. So we accomplish this by partitioning the domain of G according to a partition ratio R, and R is dictated by alpha and a problem-specific parameter theta, with an initial setting for P sub 0. Each successive bid P sub I is smaller by a factor of R. Then, in turn, the bidding quantity Q sub I is determined by the difference in the threshold function G of P between each threshold price. And now we take a look at what happens when the set of bids is submitted according to our demand bidding algorithm, dembid. Now first, let P sub k be the largest accepted bid out of the set of submitted m bids. Now, by definition, the clearing price P of t lies between P sub k and P sub k plus 1. Now, since we set the ratio between each successive bid to be R, the ratio between P sub k and P of t is at most R. This is important because P sub k essentially dictates how much of the asset is procured by dembid. Here, for example, we show some reservation price Xi, and this is the amount procured by dembid using the largest accepted bid, P sub k. And for comparison, this is how much would it be procured if the true clearing price P of t was known. Now, in fact, we do prove that our algorithm is alpha times R competitive. This is notable because since R is approaching 1 as the number of bids increases, and the overall competitive ratio is approaching the optimal online competitive ratio of alpha. Now, to evaluate our theoretical contributions, we conducted experiments using energy demand traces from 338 Akamai data centers. In addition, we also factor in the usage of renewable energy sources using wind and solar renewable generation data from the National Renewable Energy Laboratory. So in this figure, we consider a 1-week period of electricity demand from Los Angeles Akamai data center, shown in blue. So this demand pattern is rather predictable, with the demand rising during the day and it's falling at night. However, the wind energy generation in red is comparatively unpredictable. And then, as a result, the net demand, which we get by subtracting the renewable generation from the electricity demand, is also comparatively unpredictable. Then for energy prices, we use an open dataset from the 2018 New York electricity market. And here are the spot energy prices on 3 different days in December. Noticeably, the prices peak at different hours on different days. So this combination of unpredictable energy demand and prices gives motivation for taking an online approach for this electricity market problem. Now, in addition to dem on and dem bid, as discussed before, we also compare against a simplified version of our bidding algorithm called sdembid, which uses a simplified threshold function. First, we evaluate the effect of increasing the number of bids varying from 10 to 18. And each data point here corresponds to the average competitive ratio of over 365 days. Now, first we notice that dem on, the blue line, does not change whatsoever, and this is because, of course, it isn't using bids at all. Now, both dem bid and simplified dem bid have decreasing competitive ratios overall, and the orange line for dem bid is outperforming the simplified dem bid. Now, this also seems to follow our main theoretical result on a relatively small scale of increasing the number of bids. Now, overall, our work evaluates the effect of several other parameters specific to the electricity market setting, and we decide to show the effect of renewable penetration rate as a representative parameter. So here, a higher renewable penetration rate is indicative of a more unpredictable energy demand. Now, due to this uncertainty, the competitive ratio for all 3 algorithms increases with higher penetration rate. So in conclusion, we designed a competitive bidding strategy to deal with uncertainty in the current price. Our algorithm dembid approaches the optimal online competitive ratio as the number of bids increases. Then for future direction, we can use data from other locations to evaluate the effect of different markets have on our algorithms. And that's it. And thanks for listening.